talking about correlated Bernoulli processes using this thing called Bruijn graphs. I know I'm pronouncing that wrong. So the aim of this research is to be able to create chains of zeros and ones that tend to cluster or stick together. So normally if you're creating a chain of zeros and ones, you might draw from a Bernoulli distribution. But the main problem with this is that each drawer is independent, and basically we want to put some sort of structure into this Bernoulli distribution so that they cluster together and we get groups of zeros and ones. And I'm going to do that using this thing called Bruijn graphs. So the motivation behind this came from looking at classification for two distinct regions. So it might be like here, I've got one region in the orange and one region in the blue. And often to model this kind of thing, people use logistic regression. And this then you have model the probability of being in one of these regions. So probability of being in this region is high. And then to get estimates of which region it lies in, you draw from a Bernoulli distribution, and then the zeros and ones correspond to either of the regions. As you can see down here, when you end up drawing from a Bernoulli distribution, you get a lot of cases where you get a misclassification, which we're calling these dropouts. And so basically the idea is I want to put some correlation so that points that are close together are more likely to be in the same region, and then we end up with a clean boundary cutoff between regions. So Bruijn graphs are directed graphs where the nodes consist of all possible length m sequences that we're going to call words, given a set of symbols. So our symbols are going to be 0 and 1, and the nodes of the graph are going to be all of the combinations that you can get of length m from these zeros and ones. So it's easy if we look at a diagram. So this is a length 2 Bruijn graph and a word length 3 Bruijn graph. Then you can see that there are two arrows coming from each node, and this basically corresponds to adding a 0 or 1 onto the end of the sequence. So if I wanted the sequence 0, 1, 0, that would be going from here to here. And you can notice that the end part of this graph, this node, then becomes the first part of the next node, which is the same here. And that's where we're spreading the correlation over our points. So the longer the word, the more correlation we get, because we're sort of dependent on more symbols back. And for each of these arrows, we can add a probability, so probability of getting a 1 or a 0, and that is going to be like this here. So you get the probability of going from word I to word J. So, as everyone's clear with Markov chain, you might have noticed this kind of looks quite like a Markov chain, but it's more of a generalized Markov chain because it's dependent on more things happening in the future. And it's actually that a one-word Bruijn graph is in fact a Markov chain. And so then we can say that a Markov chain is Markov on the word instead of the symbol. And so knowing this, we can use a lot of the kind of features or things developed for Markov chains, and we can actually generate our chains of zeros and ones in a transition matrix like this. And to create a sort of stickiness between our zeros and ones, this means we can change the certain probabilities in here. So if we want a lot of ones to stick together and have lots of sequences of ones, then we make this one high, so that's just the probability of going from word 1, 1 to 1, 1, so you get just lots of chains of ones. But also, on the alternative, if you want something that's quite structured to be 0, 1, 0, 1, then you can make this probability quite high. But it's also important to note that you can keep the marginal probabilities the same as a Bernoulli distribution. It's just the fact that the zeros and ones will now be will be clustered together instead of quite random. So this is just a little example to show it's working. So the top here is just a random Bernoulli draw with light blue zeros, dark blue ones. And the bottom here is just where we put this de Bruijn structure on, and you can see it's working because it's now, they're all got clumped together, these stickiness of zeros and ones. And there is, in fact, the same number of zeros and ones in both of these, they're just now stuck together. Okay, so this is where it gets a bit more mathsy. But I would talk through and it's actually okay once you sort of understand where it's coming from. So we can look at things like the run length distributions. This is going to be the runs of consecutive ones together in a run length. And so this is the run length distribution for a word 2 length de Bruijn graph. So if we're just looking at a run length of 1, we start at the word 0, 1 and transition to the word 1, 0. So that's the sequence 0, 1, 0, and that gives you your run length of 1. But then if you want run lengths of 2 or more, you start with 0, 1, transition to 1, 1, and then keep transitioning from 1, 1 to 1, 1 so many times for how many length ones you want until you hit this first 0 here and transition to the word 1, 0. So you may notice this looks a lot like a geometric distribution, and it kind of works the same because we're just counting the number of successes until we hit this first 0. So even though this looks a lot worse, this is for word lengths of 3 or more, it is still doing the same thing. The main difference is that we get a lot more of these starting words that we can start from, because of whatever the word length is, as long as the last 2 symbols are 0, 1, this starts our chain of ones. So if it's like a word length of 3, then you can either start from 0, 0, 1 or 1, 0, 1 to start your chain off. So the higher the word length, the more starting positions, and then you've also got a larger run-in until we hit this geometric part here, where we're just counting the ones in, until we hit the first 0 here. So it's kind of the same, just a bit more complicated. And also to note here, just to make life a bit easier, we're using a binary notation for the zeros and ones. Otherwise, we just get huge, long chains of zeros and ones in the thing, so it's a bit complicated. So we can also do some inference. So given we're given like a chain of zeros and ones, we can write down the transition likelihood here that we can use to estimate these transition probabilities. So you've got the p's here, which are just each of the transitions, and then the n's here are how many times that transition takes place in the sequence. So let's say for m equals 2 and for larger word lengths, and then we can just use either maximum likelihood or Bayes' theorem to estimate these transition probabilities. Also given, again, a bit more maths now, but also given another chain of zeros and ones, we can also use this the same likelihood here to estimate what the word length might be to use to generate that sequence. And that is going to be using Bayes' theorem here. And so to create the posterior, we combine our likelihood with a beta prior here, which we can do because for example, if we've got the probability of going from 0, 0 to 0, 1, this is 1 minus the probability of going from 0, 0 to 0, 0. It's just adding a 0 or 1. So we can combine that and get a conjugate, find that it's conjugate because we're left over with a product of betas. And to estimate the word length, we're actually going to be using Bayes factors. And that uses this here, the model evidence, where we, next slide, because we can generate this Bayes factor for lots of different word lengths, we can calculate the model for each word length and compare them against each other to choose the word length that best represents the sequence. And it's useful to do that because if you notice, there aren't any transition probabilities in this equation here, and so it means that we can estimate the word length, and then given that we've estimated that word length, we can then estimate what the transition probabilities would have been for that sequence. We're also making an assumption here because to make the word length not too large, so we're sticking to the word lengths of only 1 to 10, calculate that for each of them, calculate the Bayes factor for each of these pairs, and choose the one that best represents the sequence. And we choose that because if the word length gets too large, then we end up with a lot of transition probabilities that we have to estimate, and it just gets very complicated, but not much added to the actual model itself. So more recently, I've been looking at a 2D version of this, which is a lot harder because it's very difficult to put a sort of direction on something that's kind of a spatial grid. So the way forward I've been looking is to actually change the form of the word, but use a very similar structure to the 1D version. So here, this would be a 1-word, 2-word, and 3-word 2D de Bruijn graph. If we're looking at the green point and which words this green point is dependent on, and each of these were formed by how many points away it was moving either to upwards or to the right. So we've got 1 point away or 2 points away. And what I've actually found looking at this is that we can actually find the 1D equivalents to each of these 2D words. And we can do that by, as long as you can write these down in a vector, and as long as we've got the ordering right, then we can treat it as if it was the same as a 1D version. So a 1-word 2D de Bruijn graph is a 2-word 1D de Bruijn graph, and a 2-word 2D de Bruijn graph is a 5-word 1D de Bruijn graph. And that means that I can do all of the inference I did on the 1D case, but I've now applied to the 2D version. And because I can do that, it should hopefully also be extendable to n dimensions. And this is just a little example. So the right here, these were made using just a random Bernoulli draws, completely random, and on the left here is where we put some of this de Bruijn structure in. So the top two here were made using a 1-word 2D de Bruijn graph, and the bottom here is a 2-word 2D de Bruijn graph. So you can see on the left here, we're definitely getting this quite clustering structure where these zeros and ones are tending to stick together. And there are equal numbers of zeros and ones in these plots. So we can definitely see that this de Bruijn structure is doing the kind of thing that we want to look at. And then kind of just a little extension of what I've been working on quite recently is that we've been thinking, especially in this 2D version, it doesn't really make logical sense to put some sort of direction on a spatial grid. And so we've been thinking how to take the direction out of the de Bruijn, but keep that de Bruijn structure in it. So we'd be looking at trying to change the form of the word. And so if you look here, same when we're looking at the green point here, we decided to have each word on either side of the green points. And so we're taking away the direction. So the red points here would be what we'd have for the 1-word, and then the 2-word and the 3-word. And because we can write it down like this, we actually find that we can use the same inference as we did before with the transition probability likelihoods. And even more recently, trying to look at what the 2D version would look like, what would words look like in a 2D in this sort of thing. But as you can see, there are a lot of different options of what these words could actually be. So this is just 2 that I've been thinking about. And on the left here is the kind of diamond shapes of the words, and these are all words made from walking along the grid and how many points away these are. So this is the 2 words, so it's 1, 2 points away, or 1, 2 points away. And on the right here, this is actually formed using the Euclidean distance. So choosing the points to go in the word that have the shortest distance from the point that we're interested in. And yeah, that can create some quite different shapes and what these words would actually look like. Okay, so in conclusion, just showing you how we created these chains of zeros and ones that have this correlation using Bruijn graphs, and looked at things such as run length. Using that, we can also find expected run length variance generating functions. And I'm looking at the 2D version and how to take the directionality out, and hopefully at some point in the future actually apply this to some actual classification problems.
Any questions for Louise? Danny?
So I was thinking about how this would apply to land use stuff, because the 2D thing is super cool. Yeah, I mean, it's really nice process. You can actually infer the probabilities. Is really nice. I wondered, how would this extend to not binary, but a finite but small number of different classes? Like arable and
I suppose when I was looking at my old stuff, we were looking at whether it was in sort of in one region and not one region, and then splitting that into binaries. So I don't know if you could split it into lots of binary
like have a nested
things.
Yeah.
So that could be a way forward, or not sure else. Or I guess putting it to binaries or things or something. I'm not sure. But
Or like multi-node. I mean, yeah, but I don't know if it extends to multi-node.
I think there are Markov models like this. Is a generalization of a Markov model.
Yeah.
So I think ecology probably has that sort of Markov model, and it could be generalized in a similar way, I suspect. We haven't tried it.
Kimpton graphs, you'd have to call those. They're completely new.
So I find that very interesting. Do you see this as a sort of refinement of, for example, the kind of issue you might address very simply with a logistic regression model? Is that what you're ultimately trying to do?
I think, yeah, the kind of, because I haven't really looked at any of the actual using this, I just sort of developing this, but it all stemmed from looking at the logistic regression and having this problem. So it basically would fill in this step here, so that we have a clean cutoff of a boundary instead of this quite a lot of noise of where we know it's misclassifying. So putting some sort of distance correlation in to stop that from happening.
Okay. So I mean, yes, you could apply it to land use, but the other obvious area that comes to mind to me seeing that is looking at species distributions, because there is a huge amount of 0-1 type species distribution data.
Okay.
So that would be a very interesting application area to look at, and I can put you in touch with people who work with those kinds of data sets.
Oh yeah, that'd be great.
This might be a silly question. When you present the motivation and stuff like that, you immediately think about correlation, like dealing with spatial correlation in a logistic model, and try to deal with that clustering. But when you talk about determining the word length, I just wonder whether that could be some sort of temporal lag, because I'm not sure in the sense that, you know, in the spatial correlation, some species might be more highly correlated to the neighboring areas, and the neighboring areas in the way that determine the length of the word. But it could also happen that there is a sort of auto-regression if you have space data, but you also have temporal data as well.
Yeah.
That if, that the present is present that year, is more likely that it will be present in the years before, or something else. So it's or any particular crop in the landscape, so more likely they have it. So there are also some possibilities applied to maybe to apply temporal data as well.
Okay, yeah, might be something to look at.
Yeah,
with
to
this,
me,
yeah.
because that,
More general.
Okay, let's thank Louise again.